record. Ritvik, you can start sharing.
Yes, sir. I have started. Are you able to see my screen?
Yes. I think I'm seeing your name, RR.
My screen is not visible.
No, you have to share from the share window. You have to select desktop or particular screen.
Yes, sir. I have selected.
No, I don't see your screen.
Let me try. Let me try again.
Yeah. So Arnab, have you joined?
Yes, sir.
So after Ritvik's presentation, so I'll request you to present the cadence part.
Okay.
So
Yeah,
is my
Ritvik,
screen visible?
I can see now.
Okay. So we'll simulate a basic CMOS inverter. So as we know that a CMOS inverter consists of a PMOS device and an NMOS device. So I'll keep on explaining as and when we proceed. So first of all, I create a new schematic file, Control N, in LTSpice. Okay. So if we want to add any component, we go to this symbol, which resembles AND gate. So I just click on this component. We will select NMOS 4. So I just select NMOS 4, okay, for an NMOS device. Again, I go to component and now we'll select PMOS 4. Okay. We'll need a supply voltage. So I just go to that component window again and I select voltage. Okay. Its other terminal will be connected to ground. So we need a ground here. And also we need a ground to connect source of NMOS. Now
so
let us make the connection.
presentation is like frozen. We are still on the component screen where you're selecting NMOS.
Okay. Are you able to see voltage source and ground I have added?
No, we're still on the select component symbol and your cursor is on NMOS 4.
Okay, it is frozen.
Could you reshare again, share again, so that I think that there might be a problem.
Let me know if it's visible.
Now, sir, visible.
Yes, sir.
Okay. So through this component window, I added a voltage source. Okay, and this triangle symbol here resembles this stands for ground. So we need a ground to connect the voltage source, and the source of NMOS will also be connected to ground. So I have taken 2 grounds here. Now to make connections with the help of wire, this is the symbol. We'll use it to make connection. So I'm connecting the source of PMOS to supply voltage. Other terminal connected to a drain. All the MOS devices will be connected. Now I'm connecting source of MOS to ground. Being a CMOS inverter, both of its gate terminals are tied together, which will take
Sir,
9 volts. So I'm
the
just
screen
connecting
is stuck
gate of
again.
both the devices.
Sir, your screen is stuck again.
Okay, I think it's again frozen. Ritvik.
Okay, sir.
Ritvik, we can't hear you.
Hello? Hello? Can you see my screen now?
Yes. Yes, we can see, but I think it's frozen again.
I've just added a voltage source at the input. Can you see that?
No, sir. Now it's there.
Fi should be.
Okay. Actually, let me draw the circuit first, then I'll explain. Maybe it will work.
Or Ritvik, you can go to the specific part of your video and then show the screen.
Okay, sir.
Yeah, you already have the video, so please go to that part. So we have already recorded certain videos by the TAs, and we are going to share all of them. So that is for your reference. But you should, if you have questions, this is the opportunity in the class to ask questions and understand if you have doubts.
So I've just saved the schematic file.
Ritvik, your screen is very slow and lagging. Hello, can you hear me, Ritvik?
Yes, sir.
Okay, so let's see whether I have your video over here with me. Yes, I have your video. So I can play the video and you can keep explaining from there. Okay, I can share my screen instead of you sharing the screen.
Sure, sir.
Okay, so you can stop sharing. I'll change the properties and then I'll share my screen.
Okay.
Okay. Okay, I'm going to share my screen now. Okay. Okay, can you see the screen? Ritvik, can you see my screen?
Not yet, sir.
Okay, now?
Yes, sir.
Okay, can you see the slide?
Yes, sir.
Uh, can you hear the audio as well? Can you hear the audio? Can you hear me?
Yes, sir.
Ritvik, can you hear the audio while I play the video? Hello?
No, sir, we are not getting any audio.
Okay. Okay.
I think there's an option to allow the computer audio to be played through video, I think, in Teams.
Okay. Where is that option? Do you know?
When you screen share, there is like a toggleable switch which you can select to select computer audio as output, something like that. So not here. When you'll restart screen sharing, then you'll get an option at the bottom of the box, which you'll have to check to share the audio as well.
One second. Okay, no problem. I will explain it. So, Ritvik, can you hear me? Ritvik, I think he has some problem. So, no problem. So, I will explain this as we go along. So, here we are seeing an inverter, CMOS inverter. The upper one is the PMOS and the lower one is the NMOS. So, this is the standard circuit you must be aware of. So V in is the input, V out is the output, and VDD and ground are the power supply terminals. So we'll use LT Spice. So this is the blank screen. And we'll have to draw that schematic through LT Spice first. So if you go to File, New, you will new schematic, you find this empty screen. You can start saving it, saving with some name. You have to go to this part, which is this AND gate like symbol called component. You will find a library of all the components here, which are available in LT Spice. So we have to take one component at a time and then put them on the screen. So first a voltage source has been added, then different components are there. We have to select NMOS and PMOS. You go again to the library and then take NMOS this time. NMOS 4 and simple NMOS means, so the MOSFET with 4 terminals, MOSFET typically have gate, drain and source, but there is also substrate terminal. So NMOS 4 or PMOS 4 means substrate connections are possible. To use wire to connect the components. So this is how we have to connect for CMOS inverter circuit. So ground must be connected with the inverter, also with the power supply. So whenever you use that symbol, that means all the grounds are at 0 volt. All those triangular symbols are 0 volt. So you have to connect the substrate of PMOS to the source terminal, which is VDD, and substrate of NMOS to the ground terminal, which is again source. So here the power supply and the MOSFETs are connected. You have to change the properties. Here you have to assign 1.8 volt. Why 1.8? Because we are going to use TSMC 180 nanometer subsequently in cadence. So for 180 nanometer technology, that means all the transistor lengths should be 180 nanometers approx. And this 1.8 is the standard voltage or supply voltage for 180 nanometer MOSFETs. So if you apply more voltage, then your MOSFET may not be able to handle it. Depends. But lesser voltage is possible, but again, you cannot come and apply 0.4 volt or 0.5 volt and then use as a VDD. Usually you have to consider the threshold voltage as well as other parameters of the MOSFETs for determining this supply voltage. So 1.8 is standard for 180 nanometers. So length is set at 180 nanometers for the PMOS, and the width should also be set accordingly. So based on your design requirements. So you have assigned W and L for both the transistors. So you have to apply an input signal to the inverter. So you have to select again another voltage source, but this time the voltage source requires to be different. It should be pulse. You go to advanced because you don't need simple DC source, rather you need V pulse or pulse signal. Look at various parameters here. So V initial, V on, that means pulse should start from 0 volt and go up to 1.8, and again it will come down to 1.8. And we have to set the timing parameters like T on and T period. Let's look at the values. Okay, so here look at the timing. So here I want to see some differences. Your circuit may be same. You have to redraw the schematic from by looking at such videos. But for selecting V on and V initial, again it will be standard 0 and 1.8, or you can select other way around 1.8 and 0 for V initial and V on. Just you can exchange the values. But both of them cannot be same values. Both of them cannot be arbitrary values, any value. It should be either combination of 0 and 1.8 or 1.8 0. But there could be many other options for T on and T period. T on, T period are the timing. T period is the cycle for one input pulse, or total cycle time, total time period for one single pulse or clock pulse. And T on is the time over which it will remain at logic 1. Okay, so for 0.5 millisecond, this V pulse should show you 1.8 volt, and then for another 0.5 millisecond, because only 0.5 is remaining after this 0.5 T on, it will remain to logic 0. So for 50% time, it will be 0 volt V initial. For 50% time, it will be 1.8 volt, which is final voltage. You can have different combinations of T on and T period. You can have T on equal to 0.2 millisecond and T period equal to 1 millisecond. But make sure your T on cannot be larger than T period. Okay, it should be always smaller. Otherwise you cannot have a pulse properly implemented. So once you have this V pulse parameters are coming around V2 and it's written over there. You complete the connections. So you can label the nodes. So you can give names to the nodes. Labeling means naming. So input node is labeled, and then you go to again label net name and then give out or V out, whatever you want. So these labels are given, are assigned to those nodes. Now he's connecting a load capacitance, because in any integrated circuit all the pins are connected and the pins are a combination of resistors and capacitors. So here he is considering only capacitance as a load. Now you save the schematic after connecting this. Look at this schematic. So what he has done, he has drawn a inverter, applied a DC voltage, also applied a pulse V2 pulse voltage as the input, and a load capacitor C1 of 1 pico. So it can be the other values also. Again, with the load capacitance value, you can try changing the value. Do not come to microfarad kind of values, but within pico or femtofarads, you can always play around for the capacitance, and then you'll find different or slightly different waveforms, and that's what we are going to look at it in your report. Now the next step is, once the simulation the schematic for simulation is done, the next step is assigning the parameters for simulation. For assigning the parameters, you have to go to simulate and then edit simulation command. Simulate is available in the menu on the top left, and then if you go to edit simulation command, you will find all these options: transient, AC analysis, DC sweep, noise, DC transfer, and DC operating point. So all those are the names of different types of simulations, different types of circuit simulations. So we'll do transient simulation first, which is the easiest one. Transient means time domain simulations. So you have to assign the parameters here. So 5 millisecond means up to 5 millisecond will do the simulation. Now if you run the simulation, run means towards left. Yeah, so this is the probe that comes. It shows the input waveform. So ideally, clock pulses always have certain finite rise and fall time. That's why the lines are slanted. Look at the red curve on the top and the bottom lines also. So that indicates the input waveform, V in. Now the probe is clicked at the output node also. So if you click the output node, you will find an opposite voltage or inverted voltage, which is in blue. So I'll play this again. Look at the points on the schematic where Ritvik is clicking with the probe, the pen-like probe, red colored. Yeah, in click it, input waveform is coming. So up to 5 millisecond, because stop time was 5 millisecond in the simulation command. Click, and then output signal comes. Now we will plot the transfer characteristics of this inverter. So what is a transfer characteristics? Transfer characteristics is a relationship between output and input voltages. Okay, so remember what was the transfer characteristics that you have studied earlier. So that you have to basically plot through the software. Okay, so we have covered this. So So I'm just replaying some part. For transfer characteristics, you have to stop the simulation first. Click on run. So you right click on the time axis. So quantity plotted should be changed to V in bracket in. So in is the name of the node, input node. Okay, V in bracket in. So that is your x-axis. So for the y-axis, you just select on this schematic with the probe. So y-axis is V output, x-axis is V input. Okay. And how you did that? Initially, time was showing on the x-axis. You right-clicked, and then over here you have changed it to V bracket in. And you can also do the same thing: right-click V bracket out on the x-axis. But instead, Ritvik just clicked with the red probe on the output node. So this is the transfer characteristics that comes through the simulation. You can draw basically a line from 0 to and 45 degree, or basically 45 degree towards upper right, that is in the first quadrant. It will have an intersection with this curve at some point. So now you can see multiple curves here. That might be due to the multiple iterations the software is doing. Right click. He's changing the width. Okay, so by changing the width, the strength of the transistor is changing. That means the current handling ability is increased from 4 to 10 due to 4 to 10 micron. The current handling ability will change. So by running the simulation again, you can see the plot gets shifted slightly. You can change the strength of NMOS also, the width of NMOS essentially. So you have to run it again. See the curve shifts. Okay, so just by changing the width of the transistors without changing L, you can always have an influence on the transfer characteristics. So transfer characteristics essentially shows how good is your inverter at different for different sizes of the transistor. So this is how we do sizing in integrated circuits. We design some circuit by using some schematic topologies, or basically some connection diagrams. But after doing that, you can always play around with the width of the transistors, whereas the length of the transistor, should be constant over the entire chip. So you have to play with the W such that you can actually work on different current levels or biasing conditions, or even the handling, I'll say, the intermediate node voltages and also the branch currents you can control by changing the sizing. As a result, your overall characteristics or overall performance of your circuit will change. Okay, so that is something about the CMOS inverter. So do you have any questions you can ask?
Sir, initially you gave the voltage to be 1.8 volt, but how did you get the range
please repeat.
0 to 1.8? Like you gave the
Your
input
voice
voltage
is very feeble actually. I cannot hear you properly.
Can you hear me now?
Slightly better, but still very light voice, very light volume. Yeah.
Sir, like initially you gave the input voltage as 1.8 volt, but you got the entire range from the input characteristics from 0 to 1.8 volt. How did you do that?
0 to 1.8 volt. In the transfer characteristics, you mean?
Yes, 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 sir.
Okay. So let's go to the transfer characteristic part of the video. Okay, so in the transfer characteristics, our x-axis is input voltage and output voltage is on y-axis. Okay, so our range of voltage over which the inverter should be characterized is 0 to 1.8 volt. Okay, because 1.8 is the maximum voltage, supply voltage, and 0 is the ground or reference voltage. Same thing for the output, the range is again the same, 0 to 1.8 volt. But the point is, look at the, if you remember the transfer characteristics of inverter, CMOS inverter, or any inverter circuit by using NMOS or PMOS, you will find that in one side, let's say while input is 0, for NMOS actually this happens, while input is 0, that means the NMOS is off. That means lower transistor is off. So the upper transistor is on at that time. That means PMOS is on. And while the PMOS is on, the output is equivalent to the voltage which is close to the VDD voltage. Okay, so your output is 1.8 while input is 0. So that means input logic is logic 0 and output logic is logic 1. But as you, this is a digital circuit, inverter is a digital logic circuit, so you don't operate in between in general. But if you come to other extreme, like 1.8 is your input voltage, at that time your NMOS is fully on and PMOS is fully off. So at that time your output is close to 0 volt. Okay, so your input is 1.8, that means logic 1, and output is 0 volt, that is logic 0. Okay, so that means the logic functions has been met by using this CMOS inverter. But in the middle, all sorts of analog changes are happening. So you get to see some slopey line and curvy lines, and then it actually rolls over, and then it finally reaches 0 volt. So you don't operate the CMOS inverter in between let's say 0.4 to 1.5 or so. So between 0.4 and 1.5, so this is the noise margin that you can consider. Okay, this is an undefined region, or you can say that this region is not allowed for an inverter to operate. So you should make a quick transitions. For that to happen, if you remember the transient waveform, this waveform, so there is a finite rise time and fall time. Ideally we need rise time equal to 0, fall time equal to 0. Practically, definitely there are limitations. You have to charge and discharge a capacitor, and that is why you get a rounded edges. So if you look at this waveform carefully, red is the input, right? So red is relatively sharp, although it has some rise and fall time, but it is relatively sharp at the edges, at the corners. But the blue one is relatively curvy. That happens because of the capacitor. If you increase this capacitance C1 from 1 pico to 2 pico, for example, you'll find more roundish kind of waveforms at the blue edges, at the edges of this blue waveform. And if you reduce this to femtofarad, then it will be much closer to your input red waveform. Okay, but obviously inverted, but the edges will be much sharper as compared to the blue one. If you decrease the value, if you increase the value of C, then your edges will be roundish. Does it answer the question?
Sir, I actually asked how did you change the voltages from 0 to 1.8 in the LT spice?
Oh, how it is done. Since you have applied 1.8 volt as your supply voltage, so the simulator is intelligent enough to assign that value. So for the time, you have to assign that time. But for the transfer characteristic, you don't have to assign the timing, or rather, you don't have to assign the voltage value. It is automatically taken by the simulator, because this is the maximum range is 0 to 1.8. Because within the schematic, your minimum voltage is 0 and your maximum voltage is 1.8 if you consider even V pulse and V1 together. So that's why it is 1.8 on both sides. So V input is always between 0 to 1.8 through V pulse, and the V output is dependent on the supply voltage V1, which is again 1.8. So automatically it is taking 0 to 1.8 on both the axes. Okay, any other question?
Sir?
Yeah.
Sir, how did we fix source and drain in PMOS over here while plotting? Means we attach the base of the PMOS to source which is above, right? How did you
PMOS
decide?
doesn't have base. First of all, PMOS doesn't have base. It is only having gate, right, at the input side. Now, how do you assign source and drain, you mean?
Yes, sir. So
Okay.
there is a body substrate as well, right? Means body substrate.
No, the substrate is in the middle terminal, which is shown by this arrowhead, either going in or out based on NMOS or PMOS. But in standard MOSFETs, source and drain are interchangeable because it's a symmetric device. But if you consider the 4-terminal MOSFETs, in that case, the substrate is closer to the source terminal. If you look at the cross section of a MOSFET, of a 4-terminal MOSFET, then the substrate connection is done through doping of one of the semiconductor layers next to the source terminal, and you have to short them. So let me find out
Yes,
a
sir.
cross
So
section
here,
diagram. Yeah. Yeah. Question. Tell me.
yes, sir. So here, the above, the first terminal is source. You were connecting body to source, right? Means we want to connect body to source. So is it mentioned earlier itself that the source is the first terminal, means the above terminal on the diagram?
Yes, yes. It is basically while it depends on the cross section of the diagram. Let's see if I have such diagram from the net. I'll try to find out one thing and I'll explain from there. Otherwise, yeah, I got your question. Let me find out the diagram. If you look at this diagram, this is the correct or relatively complete diagram of a MOSFET. Although it is not very accurate, but it is almost good enough to explain. Look at this. The substrate connection is not coming from the bottom side. Rather, the substrate connection is coming from the top side of the chip or the wafer. And this substrate is highly doped, that you must be knowing. And obviously, this is n-channel MOSFET, so there are source and drain things. So the distance of the substrate is different from the source as compared to drain, right? And these two are close by. So whichever terminal is closer to the substrate connection or the doped area of the for the substrate connection, so we call that as a source, and that is already defined by the manufacturer and also defined in the schematic symbols in LT-SPICE for NMOS 4. Does it
But
answer the
the
question?
system is symmetric, right? The MOS is symmetric.
Repeat. I can't hear you properly.
Yeah, for simulation purpose, source and drain are interchangeable.
Yes.
Yeah, they are decided by the direction of current flow or the charge carriers flow. So for simulation purpose, they are interchangeable.
Yeah. Okay. Any other question?
Sir, but in the simulation, wouldn't connecting the body to the source matter? Means if you are interchanging drain and source anywhere in the simulation diagram?
Yes. Yeah, it matters. If you interchange with the drain, then what will happen? You just think from the circuit's point of view. Let's go to this diagram. Okay. So you have to short. So in our schematic, we are shorting the drain terminals for the PMOS and the NMOS, right? Now you're saying that if I short the substrate to drain instead of source, what will happen? Very good question. So if you short with the drain, so what is going to happen? In fact, first of all, you have to understand what is there around around this source or drain regions. There are depletion regions around the source and drain. Okay, so while the channel gets formed, and if you go beyond threshold voltage or VDS saturation voltage, what is happening? You get a huge depletion region over here. So this is P and this is N, and this junction is going to be reverse biased, and the reverse biased voltage will increase if you increase the biasing of the MOSFET beyond VDS saturation, VDS sat. So at beyond VDS sat, the depletion region pushes the channel. As a result, the channel gets tapered and thinner. So there is a pinching off process that happens, and due to pinching off, basically you get a very large electric field within this pinched off region. Okay, so that is how the MOSFET functions, if you recall from the basics. Now, coming to the question, if I connect bulk or substrate to the drain, and the drain is typically at a larger voltage for NMOS transistors, okay, and the substrate, then this junction will get forward bias. So that there will be substrate, there will be huge, instead of leakage, the junction, whatever gets formed over here, it will start taking some current. So now P plus will get a positive voltage. So drain is having larger voltage, source is having negative ground voltage or 0 volt in our existing schematic. Now, keeping source as ground, and I'm connecting this P plus instead of ground, I'm connecting it to larger voltage. So what is going to happen? P plus is, and then there is a N, so there will be current flowing from the P plus, and then it will break the junction and go through, or rather it will become forward biased, and then it will flow through source. So most of the current won't flow through the channel, most of the current will go through the substrate. So that means your transistor is almost useless. You are bypassing the transistor if you connect substrate to drain for NMOS. Okay, same thing exactly happens with PMOS. For PMOS, you have to connect substrate not to ground in as in NMOS, you have to connect to VDD for PMOS, such that you don't forward bias this P in junctions. This is P. The middle region is also P because it is P substrate, and then there is N. So if you apply large voltage to P as compared to N, obviously this junction gets forward biased. So there is no point in this channel and conduction of current through the channel of the MOSFET. Okay, so therefore, for N channel, we should always connect substrate to the lowest possible voltage, and for P channel, the same substrate. So obviously, this will become N plus, and this will become P plus for P channel MOSFETs. So you will always connect this substrate to the highest voltage for PMOS and lowest voltage for NMOS. Is that clear? Is it clear?
Yes, sir.
Okay. So if you have any other question, so you can always reserve it, write it down, and I can try to answer after the class or in the next class. Okay. So we'll go to the cadence part. So I request Arnav to share the screen and go for cadence. Start with the cadence simulation explanation.
Okay, sure.
So I'll stop sharing my screen. I'll give you permission also.
Sir, I need the permission.
Arnav, you can start now.
Okay, sir.
Excuse me, sir.
Yes.
Sir, where will we get the questions or like the problem statements for the homework assignment?
I'm going to circulate that.
Okay. Thank you, sir.
Okay, so this is now you are getting a tutorial on how to use the software tools.
Yes, sir.
I'll give you. Okay.
Can you guys see the screen? Hello?
Yes, I can see the
Yes.
screen. Yeah.
Yes, sir. We
Okay.
can see.
Okay. So this is the cadence window. So this one is the main window, the CIF editor window. So if you want to create a new library or a new schematic, you have to go here. So can you hear the audio?
Yes, sir.
You can hear the audio from the video?
No, sir. No. I
Okay.
thought you meant your audio.
No. Okay, no problem. Okay, so in order to create a new library, you have to go to File and so go to File, New, Library. You have to give a name to the library. So in this case, we'll give Lab January 21. And you have to attach this library to an existing technology node. So in this case, we'll be using the TSMC 18 node. Press OK.
So this is 180 nanometer TSMC, which is called TSMC 18. We call it a node because that's a usual practice people follow in industry and academia. So 180 nanometer node. That means all L will be 180 nanometer.
So this is the TSMC 18 is a TSMC 180 nanometer node. So the minimum L, that is 180 nanometer. So you can go greater than 180, but the minimum length of the transistor is 180 nanometer here. Okay, so our library is created. Next, we will create a schematic within this library.
Ignore the background because that was from something else. Okay.
Oh, this background is some other schematic. So you have to ignore this. So you'll go to File and create a new schematic. So we'll go to the same library we have created, Lab January 21. We'll name our schematic inverter. So this is a schematic editor window. This is a blank window. So you'll create all your schematic inside this window. So like the previous experiment, we will have to place a PMOS and an NMOS. So a PMOS and NMOS will be within the TSMC 18 library. So we'll again go to that library. So here in this case, PMOS 2 volt is our 1.8 volt MOS. So you go to TSMC 18, write down PMOS 2 volt, PMOS 2 volt will come. So in order to go there, you have to press I to instantiate. So in order to place any symbol in the schematic window or in layout window, you have to press I. I will open that search window and you can search for the particular symbol and place it on your schematic. Similarly, we will place the NMOS again by pressing I. Now, in order to change a property of any transistor, all you have to do is press Q. You select that particular symbol and press Q. And here you can see all these properties. You can change the W, you can increase L if you want, but the minimum is 180, minimum allowable length. So here I will keep the PMOS with double that of NMOS, since the mobility of holes is almost equal to half that of electrons. Now we need to connect the nodes. In order to connect, you have to press W to create new wires. So we'll connect the gates of the PMOS and NMOS together. The drains of the PMOS and NMOS together. We'll connect the body and the source of the PMOS together and connect it to the highest potential. Similarly, for NMOS, we'll connect the body and the source together and connect it to the lowest potential. So the central terminal is the body terminal, and you have to connect this together. For NMOS, it is compulsory to connect the body terminal to ground because it is a two-well process. But PMOS, you can keep the body terminal at a different voltage, but you have to be careful so that there is no extra current flowing between the two nodes. Now, in order to simulate the circuits, we need sources. So we will now select the sources. The sources are located in analog library. You have to go to analog library. So first we'll place the ground. So whatever you need, you just go to the library and type that particular. For DC source, it is VDC. We'll place a VDC. This is for our ground connection. We'll need another one for source connection. Sorry, the supply connection. In order to copy any particular symbol, you just select that particular symbol and press C to copy. Next, we'll need a V pulse. Again, type V pulse. A V pulse will appear. Now we'll connect the sources. We'll connect the lowest terminal with the ground and give this voltage 0 because this will be our ground alias. So in order to name any particular wire, press L and write the name you want to give. So here we'll call this ground wire ground GND. We'll press L and write ground and place it on top of the wire. We'll connect the ground to the other sources. Next, we'll define the VDC. Since this is 1.8 volt MOS, we'll keep a supply voltage 1.8 volt. V pulse will define the pulse width. For one phase, it will be 1.8 volt. For other phase, it will be 0 volt. So we'll define the period as 20 microseconds and the pulse width as 10 microseconds. Again, we'll name these particular wires. We'll call it VDC. Just press L, type the name you want to give, and place it on top of the wire. We'll call this V pulse as Vn as the input pulse. Now we'll place this particular wires on our main schematic. So the advantage here is you don't need to connect physically to sources. So if you have multiple requirement for the VDC at multiple points, you can just call this wire name and it will automatically take the 1.8 voltage. Now in order to simulate the circuit, we will need to use a tool called ADEL, which is a simulator, which is a simulation tool. The simulator is Spectre. So we'll use that ADEL tool. And because we want to see the time domain analysis of the inverter, we will go for transient analysis here. So this is a transient analysis. Just we'll select for 10 periods, 200 microseconds. Now there are different options: conservative, moderate, liberal. Conservative means your step size is less, so there will be more number of steps. For liberal, the step size is large, so less number of steps. And if you want an accurate simulation, you should go for conservative. Now, so we'll go for conservative here because it's a small circuit. It will not take a lot of time. Just select the conservative, press OK. Now next we have to select the input node and output node from where we want to see the input waveform and output waveform. So this is the selection window. You have to press here. This will appear. Select from schematic. We'll select V in, V out. Okay. And in order to check and save the circuit, so before you run the simulation, always do check and save. You can press short key X to check and save, or otherwise you can go to File and do check and save. So when you run the simulation, you get the input and the output. So the top one is our output waveform. The bottom one is the input. You see that the output is the inverted form of the input signal. Now in order to again do the transfer characteristics, so I haven't done it here. What you need to do instead of a V pulse, you will have to give a VDC and run a DC simulation, and you have to sweep that DC voltage. So there is an option of component parameter sweep. So you have to select that component and sweep the DC voltage from 0 to 1.8 volt, and that will give you the transfer characteristics of the inverter. So this is it for the first video.
If you have any questions, please ask.
How does the purpose of using these two softwares differ? I mean, both do the same thing, right?
No, see, LT-Spice is a freely available software. Cadence is a commercial tool to fabricate integrated circuits. If you want to fabricate ICs, you have to use Cadence. And if you want to check your circuit, see if it's working properly, LT-Spice is good. But there are a lot of components which are not available in LT-Spice, and there is no foundry support as well. Also, in LT-Spice, you cannot run big simulations. And another important thing is schematic is half of the overall thing. You have to do layout. So in LT-Spice, I don't think you can do layout.
Yeah, so we generally teach this lab through Cadence, but this online semester doesn't allow us to give you access to Cadence from outside the campus, as I told you right at the beginning. So that is why for the first time we are doing LT Spice for this particular lab course, but we don't have any other option. So we have to do lab assignments and homework on LT Spice only this time, but Cadence should not be ignored. So we are going to give you these videos and tutorials such that if the semester reopens with you coming to the campus, if that happens, then this tutorials on Cadence will be useful for the lab part of this experiment, real lab experiments inside the lab premises or our IIT premises. But for now, LT Spice and Cadence, both videos will be used for Vivas. Okay, so that is very important. So you have to consider both of them together. Until now, there is no difference. But as Arnav said, that there are lots of differences, as he correctly pointed that this is a commercial and professional software. So all the integrated circuits that you see in your television sets to mobile phones to each and every gadget like smartwatches to everything, almost all of them are designed by using Cadence software. Okay, and obviously there are other tools in addition to Cadence, so sometimes combination of them are used.
What exactly is layout like?
So layout is that so once you design a schematic, so inside the chip you see it's you have to place your transistors in a physical form, right? So the layout, what it does, you have to create a physical view of your entire design. So just you can as a assume it to be the physical view of the design for the time being. So once we go to the layout, I'll explain it in more detail. So you cannot tape out the schematic, right? The schematic is just a symbol view. It's just an abstraction of your circuit. So in order to tape out, in order to fabricate a chip, you need some physical view, where the foundry will create the mask definition. So that is where you create the layout.
Okay, Arnav, I think we are going too deep into this for this particular course. So, in short, layout is the real implementation of transistors and the connections as per the schematic. So, the schematic thing you have seen NMOS and PMOS. So, we have used 4 micrometer width in one case, and other case was 2 micrometer width for the LT Spice side. But in reality, what does it mean? So that means the size of the PMOS is double in width as compared to the size of the NMOS. So that means if you draw 2 transistors side by side in layout, you'll find 2 different sizes based on their selection of parameters. And secondly, in addition, those connections like VDD connection, input connection, output connection. So all those connections are also done through metal traces, some metal tracks, and those layout means basically how do you arrange those tracks, how do you arrange the transistors and connect them between each other. Okay, so layout we'll do in the next class in the for cadence about the layout part, or we can Arnav, can you do it today also?
We can do it today.
Okay.
So next
So
part is the symbol view creation. So
yeah, so symbol view creation is there, right?
Yeah, so
So
layout
we
we
can
can do next week.
Yeah, so let's do the symbol view creation today and then the layout. So in brief, so what is symbol view creation? Arnav, you can set up the video. I'll start explaining the introduction. So the point is, what is the symbol of a NOT gate? The symbol of a NOT gate is just a triangle with some bubble in at the beginning. I know Arnav's video will not show you the exact triangle and the bubble, but he will show you how to create a symbolic view. Suppose you are designing a very large circuit which requires, let's say, hundreds of inverters. And how you are going to draw such a large schematic? So it is not recommended to draw 100 into 200 transistors and show all the connections in between. If you look at this CMOS inverter, so 1, 2, 3, and 4 connections in this basic form, along with 2 transistors are there. So there are 4 wires and 2 transistors. So if there are 200 inverters, there will be 200 transistors, and this 4 into 2, that is basically 4 into 100, that is 400 wires should be drawn manually. So that is a wastage of time and resource, and also it is not very efficient because there is an error prone approach. Because while drawing same thing, you can copy paste always, but the copy pasting may also have difficulty in reading or interpreting the circuit in a large schematic. So it is better if you draw a symbol, something like a symbol of a NOT gate, and whenever you instantiate or whenever you use that symbol, that means there are 2 transistors and these connections inside that particular symbol in a hidden form. So the performance of that symbol in the NOT gate symbol will be same as the performance of this exact circuit with this selection of transistors and their properties. Okay, so we have to generate symbol, something like if you are drawing a symbol of a transistor, even inside the symbol there are internal parameters. Actually there is a code, there is a spice code that or script which actually represents this transistor, this arrow, bubble, etc. for the PMOS, and the arrow and other arrangements for the NMOS. Okay, so symbol is just when makes your task simplify your task in a very large circuit. So Arnav, you can start now with the symbol creation.
Okay. So we'll start with our inverter we created last time. So in order to create symbols, the first thing we need to do is create pins. So pins are similar to the pin diagrams you've seen in ICs like 741 or other digital ICs. So here we'll create pin, and in order to create pin, we need to press P for pin. So we need to give a name to the pin. The direction based on your signal direction, it can be input output. or only input, only output, but preferably give input output because these are just symbolic representation. It is not going to affect anyway your circuit. So we'll define 4 pins, VIN, Vout, VDD, and ground. Other important thing to consider is whenever you are naming a pin, name it in capital letters, because when you are doing the post layout simulation or when the post processing after layout, error comes if it is not in capital letters. So it is better to start using capital letters when you are giving your pin name. So the source pin will call as VDD. In order to change anything, you can just double click on it and just change the if there is any error. Then we will create for VIN, Vout, and ground. Just drag it outside a little bit. So again, press X to check and save. So this is the pin diagram of the entire circuit. So there are 4 pins for the inverter, 1 supply, then there is input and ground, then there is an input and an output pin. Now in order to create the symbol view, so we'll call this instance we'll just store it in a symbol view, and we can call this particular instance, this particular transistor sizing, as the symbol. So to create it, go to create cell view. From cell view, press OK. Now, so the left pin, traditionally we give the left pin as the input pin and the right pin as the output pin. It's up to you whichever direction you want to give. Then the top pin will give us at VDD and the bottom pin as ground. And press OK. This is a symbol view. So you can press delete and delete these things. These are not required. Now you can just rename it as inverter. Double click and rename it. So in some case, if you want, you can change the shape to a triangular shape, but in the simulation it doesn't help if you do triangular. But if you want to take screenshot from it, then you can do it as triangular shape. So you have to go to polygon and change it if you want to change it. So this is about the symbol. Now, like any other symbol, we created the PMOS symbol. So we can instantiate this particular inverter. We'll press I, and we'll go to our lab January library and select this symbol. So this symbol will represent the inverter as a whole. So we don't need to individually select the PMOS and NMOS again. Suppose we want to make a ring inverter, ring oscillator, which will require an odd number of inverters. So we can just use this inverters and create the ring oscillator. Yeah, so this is it for the symbol view. Any question?
Basically, within that rectangle inside, you can draw that polygons or basically some lines to draw the triangle and the circle or bubble at the end part of it. Okay, so you can draw any other shape also. You can draw any other shape, and for this one, so we are doing it for inverter. So this is just a generic block. So Arnav is showing an empty box, the rectangle, but you can draw any symbol over here, any op amp symbol or transistor symbol or any other. Generally, we don't draw transistor symbol. We draw gate symbols. We draw, let's say, A to D converter or different types of complex circuits are there that can be drawn inside that rectangle. You can change the size and so on. So symbol view is important for very large scale circuit simulations. So you can create symbols for every sub parts. Like you can design a counter and then create a symbol for a counter, and then keep it and use that counter as many times as you want later on. And then the simulation results for that original counter, which was designed by using transistors and its connections, will remain the same. And one thing to be remembered here, while Arnav started making this symbol or drawing this symbol, at the beginning, he was not considering the load capacitor, that 1 pico capacitor that was considered earlier, or even he's also not considering any voltage sources. So voltage sources are outside, or V pulse, all those things are outside this symbol. This is just the core circuit, the inverter circuit with the two MOSFETs and the connections between them. So you may have more than 4 connections also. You may have as many connections as you want based on the complexity of the circuit inside the symbol. Okay, I think we will do the layout next time. Arnav, will you be present next time for layout?
Yes, sir, I will try. Depends whether the server is working. I'll come for half an hour to 40 minutes and explain it.
Okay, so you can come initially for half an hour or 45 minutes, and then we'll cover the layout part and the DRC LVS part.
Yeah.
Okay, so there are few more, 2 more parts in the cadence portion, because since cadence is so powerful, you will have to learn certain features of cadence, which are very important. So there are different ways to analyze circuits. You can see that LT-Spice is free, but obviously it is a starting program or very simple to use program with limited abilities. Or in cadence, there are lots of ways to understand whether your circuit is going to work in real world or not. Okay, so that's why cadence was important, and we prefer cadence for this course. So you have to learn the features. I'll be uploading all these videos apart from the class recorded video, obviously that will be saved, but otherwise the videos for LT-Spice and the cadence that we covered until today I'll be uploading that. I think we can end the class now. If you have questions, you can ask me now, and I'll give you the homework by today evening or tomorrow morning, and then you can start doing that. Obviously the homework must be completed by next week. Homework will be on LT-Spice only. So if you have any questions, so you can ask me.
Sir, and there would be a lab report regarding the work that is given.
Yes, you have to write the report based on the LT-Spice side of experiments, and you have to, I'll give you a format. You have to make sure that all the reports are different, your text is different, your figures are different, your schematic may be same, but your parameters inside the schematic must be different, which is very simple. And then your plots must have different some changes from others. You cannot just copy paste, you have to re-simulate by your own, at least even if you are copying it from your friend. But copying is first of all not recommended, but in online mode I cannot stop that also. So it's up to you whether you want to gain maximum expertise or not by self practice. So that is what I want you to gain maximum experience to the extent possible. And if the institute tells us that we'll continue or complete the lab grading after May or something, then and in that case, if they are bringing all of you back to the campus, we will go to the lab and will perform the cadence experiments in reality. And LT-Spice is not just for this kind of transistor level simulations. You can use that for a lot of other simulations, but at a very basic level. You cannot do very complex simulations. Also, size of the circuit and everything else matters. So it should size of the schematic should not be very large in LD spice. Okay, any other question? Okay, I've already taken the attendance. So let's see what is the attendance now. Yeah, so I've already taken the attendance. So you can leave now. Okay, thank you, Arnab. Thank you, Ritvik.
Thank you.
Thank you, sir.
Thank you,
Excuse me,
sir.
sir.
Oh,
Thank you, sir.
yeah.
Excuse me, sir. Thank
Yeah,
you,
tell
sir.
me.
Sir, is Professor Vivek Dixit in the meeting?
I think
Uh,
he's not here. So, do you have any question for him?
No, no, I'm
I have
here.
to,
Tell me what you want.
good afternoon, sir.
Oh,
Good
he's
afternoon.
here.
Sir, actually, I had opened up a mail thread for my DSP lab slot swapping.
No, no,
It
that you
was,
have to talk to your concerned class teacher. I have no influence there.
yes, sir, yes, sir. Sir, the issue is that I've been writing multiple mails and to both the professors, Professor Mukhopadhyay and Professor Sharma, but I haven't been receiving any replies. And the lab is tomorrow, and I'm really worried that
So then you
I
attend
won't.
their lab. What's the problem?
Sir, I won't be able to attend the algorithms lab in that case, na?
You want to attend now? Which day?
On Tuesday.
Then you contact
Sorry. I want
they
to
have
attend
to
on.
attend your lab.
I want to attend on Thursday, sir.
Then
Sorry.
you contact the concerned teacher. You attend their lab. What's the problem?
Sir, actually, that I need to swap my slot with someone in order to attend on Thursday. So the person I want to swap with, he's Bhaskar Lunawat. So he wants some assurance from Professor Sharma that his work from the first lab, which we attended before swapping, would be considered, and his attendance as well. So regarding that, I wrote a mail to Professor Sharma and Professor Mukhopadhyay, but I haven't received any reply, and it's been like around 4 days.
You again write. CC me. Okay.
Okay, sir. Okay, I'll write another mail.
Okay.
So, is there any way if you can help me resolve the issue?
No, you write an email to both of them. CC me, CC MC. Okay, head.
Okay, sir. Okay, sir. वैसे if we swap our slot, so the first lab I attended on Tuesday, and Bhaskar
So if
attended
you
his
attend,
first.
it will be counted. No problem. If you're not attended, then it will not be counted.
Okay, so even if I attended the lab on Tuesday and after that I swap, my attendance will be counted on Thursday, right?
No, that concerned teacher has to inform that whether you attended or how you have attended.
So that is the problem now, that they are not replying to my mail regarding that. So unless and until they reply, Bhaskar won't acknowledge the swap on the official thread. Anyway, sir, I'll write another mail and I'll CC you. I guess you can only wait for the reply. Nothing else.
You CC him also, Bhaskar also, okay?
Okay, sir. I'll write another mail.
Means include all the stakeholders.